don't know. Talking about tiny font. Oh, where? On, like, your handout? No. I don't know. Baby font. Okay. We came out. All right, so the kids are filling in the derivatives of the trig functions. Yeah. Probably it's going to be Wednesday. Because tomorrow's the last new thing I have to teach. We'll get a review sheet tomorrow. And then we'll go over it. It's kind of long. So that's why I think I can't. I wanted to do it Tuesday, but I'm trying to be realistic here. And Wednesday. All right. Let's. So yesterday, we used the limit definition of the derivative to get the derivative of sine and cosine. But the other ones, what rule did we use to get the derivatives of the other trig functions? Like one's quotient rule, right? And once you know the derivative of sine and cosine, all the other ones you can just use the quotient rule to get. So let's see how many you actually know. Derivative of sine x. Remember that one? Cosine x. They're all singing cosine. Am I like actually on? I hope so. Okay. All right. What about the derivative of cosine x? Very nice. You weren't even here. How'd you know? Negative sine x. Beautiful. Okay. Tan x. Secant squared x. Derivative of cotan x. It's just like for if you know the derivative of secant x is secant, tan x is secant squared x, the derivative of cotan x is negative cosecant squared x. There you go. It's the same thing just with the cotrig function. Good, good. Derivative of secant x. So what do you think? Secant x tan x? Do we agree? I don't know. All right. Yeah, you're right. Secant x tan x. So the derivative of cosecant x would be, all right, that's good. Negative cosecant x secant x. And you just have to say it. When you're home alone or you're just walking around, just say these things out loud to make it really stick in your brain. And so yesterday we said all the trig functions that start with the letter C, all the trig functions that are co-trig functions, what do we know about their derivatives? They're negative, and that really helps us. But I'm telling you guys, the sooner you learn these derivatives, the better. Because you won't just lose points on this test if you don't know them. You'll keep losing points on everything. Eventually, you'll have a negative average. No, that's not going to happen. That's not going to happen. I'm just trying to scare you. I went over I just did too much. Too much with the fears. Too much. Okay. Before we get to go over some of those little practice homework problems, the 1 through 9 odd, I thought we'd have a little bit of fun. You want to have a little fun? Jessica Thomas just said, my definition of fun is her definition of fun. Thank you. Thank you. Okay. All right, now, here's a graph of some unknown function. Do not say what it is. Okay? Okay. All right, well, what I want to do is I want to graph the derivative of this function. And because we know that the derivative is the slope. So what we're going to do is we're going to start out with a few points on the graph of the derivative. We're going to start out finding the points. If we know where the derivative is 0, we can at least, we'll know those points on the graph of the derivative. What I want you guys to do is as I go along the curve, tell me when you think the slope is 0. Oh, right here. So that means that for this x value, the derivative is 0. So this point would be on the graph on the graph of the derivative. At that point, you've got 1 point on the graph of the derivative so far. Okay. My kids at home can't see, like, I'm actually moving the pen along the curve, so you just have to imagine it. And I'm going along. Tell me the next time the derivative would be 0. Yeah, I was right over here. No, it's trying to chicken. Now I'm looking at the slopes, waiting to see when it's 0 again. Right there. That would be a point on the graph of the derivative. Are there any other places you think the derivative would be 0? One more. You got it. Right there. Okay, so 4 points. That's good enough for the graph. No, just kidding. That's not a good graph, right? We need a few more points. Yeah, where do you think it's 1? Actually, if you had to just guess anywhere, like, actually there are, that's actually pretty good. I would never even thought to do that. But yeah, you see how this, if you look at the slope here, kind of follow it, it does look like it has a slope of 1 there. I'm gonna make a little point here. You don't know exactly what it is, but it could be around 1. I think you're pretty good with that. All right. It's crazy. All right, now what I want to do is we're just going to get an idea of what the rest of the graph looks like. Let's look at the very first part of this graph, up to the first 0. Let's look at the slope of our graph. Are the slopes of the tangent lines positive or negative? Positive, okay. Now, I want you to think about the magnitude of the slope. So it's a positive slope as you go along, left to right, but does it get flatter or steeper as I go along? Flatter. So the magnitude of the slope, even though it starts out like with some positive value, but as you go along, what's happening to that positive value? It's decreasing, right, and going to 0. So I don't know exactly what it looks like, the graph of the derivative, but I know it starts up, whatever the slope is here, and it decreases down to 0. That's all I know. I don't really know how it's curved at this point. I just know as you go left to right, the slope stays positive, but it's starting steep, so it's starting at a greater value, and then it's going down to 0. Let's talk about between the two zeros on the graph of our derivative. So up here we said the derivative is 0. And now, in between this point and down here where we're 0 again, are those slopes positive or negative? They're negative. So the graph of the derivative is going to be below the x-axis. Right? So it's 0 here, we got that. Now, as I go left to right, the slope's a little negative. Tell me when you think it's the steepest. We're about here, right? So it's going to be like the greatest negative value, and then the magnitude will be the greatest here. And then it'll go back, still negative, but then it gets back to 0, right? So the slope is 0 here. It gets a little negative, more negative, and then it goes back to 0 somewhere. Now let's look between these two zeros. So we know the slope was 0 here and there. How about between there? Do you think the slopes are positive or negative? Positive. So the graph of the derivative will be where? Above the x-axis, right? That's where the values are positive. And it's 0 here. It's a little positive. More and more positive here where Jillian thought it looked like it was about 1. And then back down to 0. Can you show me with your hands what you think the graph's going to look like? Between those 2 points? Yeah. So it goes right, it goes up to some whatever the positive value is, and then back down to 0. All right, you know what we're going to do next, right? We're going to try to graph the derivative of this part of our graph. Graphing the slope of this graph. So it starts out at 0. What about the slopes over this interval, positive or negative? Negative, right? So think about what the slopes would be. Think of numbers, you know, what they would be, and can you show me what you think the graph would look like over there? Oh, I'm getting a few people get it. Ryan, what kind of graph is that? Just thinking about pep rally. All right. All right, mine's not so good this time. Oh well. All right. All right. And then we're here at 0, right? And for the last little piece, is the graph going to be above the x-axis or below? Above, right? 0 and gets more and more negatives and go something like that. All right. If you had to guess what the original function, its equation was, what do you think it looks like? So our function is y equals sine x. Now we just graphed its derivative. What is the graph of the derivative look like to you? What? Is that true? Is the derivative of... see that coming? I did not see that coming. Did anyone see that coming? Oh, sorry. But yeah, it's just another way to kind of digest that the derivative of sine x is cosine x. Do you want to know the slope of the sine curve anywhere? Just take the cosine of that x value, and you'll know the exact slope. That's amazing. All right. All right, let's see this homework that you guys were complaining about. Okay. Oh. All right. Well, give me one that you got wrong. 9? You going right? Can anybody read me the actual, what the original, Cameron?
All right, it's cotangent x over 1 plus cotangent.
Whoa. And we're supposed to take the derivative of that? Hey, can't I just cancel those cotan x's?
No.
Oh, that's right. Because there's addition here, right? This is not a factor of the whole denominator. So don't even think about it, because I know someone's thinking, I did that. All right. So what are you going to do? Take the derivative of the top, put it over the derivative of the bottom? No. The quotient rule. That's it. Low to high. So we're starting low. Start it from the bottom. D high. What's the derivative of cotan x? You guys are good, I have to say. I'm actually kind of impressed. I know you have it there, but you actually care enough to... I don't know. All right, so far we have low D high, less. High D low. Oh, what is D low going to be? That's it. Negative cosecant squared x. All right, so we have, okay, we got all that. Draw the line down below. Whew. Sorry. I want to clean this up a little. Any ideas? Yeah. You could do that. Okay. So you want to multiply by 1 minus cotan x over 1 minus cotan x. So the denominator would be 1 minus cotan squared x. All right? Now, does that mean anything to you? Do you know a Pythagorean trig identity that you can... It is a thing, but it's going to have to do with cosecant squared. It's not going to make things any easier. I like that you see a binomial and you're thinking multiply by the conjugate. And that's good when you want to get rid of something. But if we do that, we will wind up with a cosecant squared. It's not going to help us making it easier. So if this is the derivative, and this is not the answer in the back of the book, I got to clean it up a little, see if I'm right. Any ideas what we could do to that numerator? Because that's just a little ugly. Anyone else want to take out a negative cosecant squared, or what else? Wait, are you talking about canceling this one? No, because if it was... Ooh. There's gasping. Yeah. It's so important, though, that you say things like that, because so many people do that. You can't cancel it unless it's a factor of the whole numerator. It's a factor of the first term. It's not a factor of the whole numerator, so you can't cancel it. If you could have pulled it out of the second term also, you could have. You see, but you can't, okay? That's when you can cancel. It has to be a factor of the entire numerator or the entire denominator, not just one of the terms. Yes. Yeah, like if you had, let's do numbers. 4 times 2 plus 5. Let me just think, what is that? So that's 13. 13 over 4. Okay, 13 fourths. That's all greater than 3. You know that there's no way that that's equal to 7, right? You can't do that. But if this number over here, instead of a 5, let's say it was, I don't know, 16. Great example. Okay? So I could just do it out. I could do 8 plus 6, 24 over 4, 6, right? If we pull the 4 out first, in the parentheses, what would I have? I have the 2 plus 4. See, now if you cancel, because you're saying 1 times anything is itself, you're allowed to do it. But unless it's a factor of the entire numerator or the entire denominator, if this is flipped, you can't cancel. Oh, but look at the good old days with the numbers. Forget that. Look at we're back with this. So we said one thing we could do was factor out the negative cosecant squared. And Tim, did you want to say something different, or is that what you want to do? No? Oh, that's good. Yeah, you could do that, or you could distribute. But I think factoring out the negative cosecant squared is just lovely. So let's do that. So what would be in the parentheses? What would the other factor be? 1 plus cotan x. What? Nice. Oh, bye. We're going to talk about you, and you can hear us talk about you later if you watch us. Okay. Look at that numerator now. Yeah, right? Which is the answer in the back of the book. Crazy. Well, then they converted everything to sines and cosines. So they said the answer was this, or if you wanted to change everything over to sines and cosines, you could do that too. No, you don't have to. No, I'm not doing that. You can only do math one way. Was there any other questions? Yeah, it should be the same thing. Yeah, those terms cancel out. Either way, you're left with this. Well, there are other questions of those 1 through 9 O's. 3? Can you read what the function was? Plus 5 sine x. Okay. So we go to get the derivative. You could, but what a waste of a beautiful rule. Instead of using the quotient rule, rewrite it as x to the negative 1 and use the power rule. You did that? Yeah. Okay, so the derivative of 1 over x, this is when you're going to take so often you just want to just know it. It would be negative x to negative 2 or negative 1 over x squared. Okay. Is that one okay? Sorry, I don't know. Now, when you go to take the derivative of the 5 sine x, you can either just leave the 5 and multiply by the derivative of sine x. And I know that bothers people. They're like, oh, wait a minute, isn't derivative of 5 0? If this was the derivative of 5 plus sine x, I would take the derivative of each separately, right? And I would add them. Yeah, this is that constant multiple rule. And if that bugs you, think of the product rule. If you considered this your first and the second factor your second, right? Product rule says you take the first derivative of the second. What's going to happen when you take derivative of the first if it's a constant? 0, right? So you'll never have that. 0 times anything. So every time you take the derivative of a product, but the first factor, that is a constant, you don't need to do the whole product rule. Just leave the constant multiplier and multiply by the derivative of the function. Okay? So anytime you have the derivative of a constant times a function, the derivative is that constant times the derivative of the function. Okay? Well, if it's a variable, it's like a function. Yeah, oh yeah, if the first factor is not a constant, it has a variable in it, then you have to use the whole product rule, the whole thing. That part won't be 0. Let's practice taking derivatives of trig functions. Come on. All right, let's do this. All right, so what we were just talking about. So Go ahead. This is taking 2 seconds. Derivative of 3 sine x. You don't have to do too much work, right? What's the derivative, guys, of 3 sine x? 3 cosine x. That's it, right? Because you leave the 3 because it's a constant multiplier. It's not added. It's a 3 times the derivative of sine x. Got it? Now, I do have a little hint here. If possible, always simplify before differentiating unless you like extra work. Okay? So if you don't want to simplify first, you don't have to. Let's look at the second one. You can just take the derivative as is, or you can try to simplify first, then take the derivative. What do you think? Let me do it the long way, this kid. So yeah, I'm going with what you just said. Yeah, when you multiply anything by its reciprocal, right? Cotangent 1 over tan, you always get 1. So you're taking the derivative of 1, which is? Okay. Yeah, or else, it will be equivalent, but just to make everything work out. You make one little mistake with the signs. That's it. All right. Oh, no. Guess we got to do quotient rule. Oh, you knew that? Like sine and cosecant are reciprocals? So when you take 1 over sine x, you get cosecant x. 1 over cosecant x is sine x. They're reciprocals. So, yeah, don't forget, you still have to take the derivative, but you say, oh, that's just the sine of x. And the derivative of the sine x is just cosine x. It's got to get harder than this. That's what they're thinking. Whoa. See what you can do with that. You can leave it as is, use the product rule, or see if you can clean it up. What are you thinking? What? When you simplified this, what did you get? Cosine x, yeah, but you're right, your final answer. So she's saying that this is just the same as cosine x. You see why? No. We're saying no. Yeah, then when you take the derivative of cosine, you get the negative sine x. Bam. All right. Let's see what else we got here. Number 5. This is fun. Oh. Wonder how you're going to rewrite that. Or else you could use quotient rule. Nothing wrong with the quotient rule, but you could rewrite this one. You don't want to? No. I just like to write it. Think about how you could rewrite that. Number 5. Okay, so then we still have to use quotient rule? Is it? No. Is there any way you could just have a constant multiplier? Like how? 1/5 what? Yeah. Because remember, you can think of your 1 as being 1 times 1, right? So you're really taking the derivative of 1/5. Remember, don't change the number. But the 1 over cosine x, that's just secant. It's the reciprocal of secant. All right, we still haven't taken the derivative yet. But now we've got a constant times a function. We want to take the derivative. You leave the constant. So 1/5, and the derivative of secant x is secant x tan x. find one that we can't simplify. Look for something hideous. Let me see. What's 6? Oh, I skipped that. Oh. This one you can simplify too, though. I want to find one we can't simplify. Does anyone know what secant over tan would be? Because that's 1 over cos over sine over cos. So that would just be taking the derivative of cosecant x, that's 1 over sine x. And what's the derivative of cosecant x? Negative cosecant x cotan x. Yeah, see, that's no fun. We could simplify that too. There is one in here we're going to get stuck soon. 8? Oh, yeah, because this one, too easy. If we simplify this one, what is it? 3 over cosine x is the same thing as 3 secant x. So what's the derivative? All right. All right, but 8, you promised me we're gonna get stuck?
Yeah.
Okay, good. Because I don't want you guys thinking that you're always gonna be able to simplify. You know? Oh yeah, this is good. That's a good one. This is good. And that's an x over 4 over here. That's, I know it's written next to each other here. X over 4, that's what that's. All right, so we're not going to simplify. Don't even try, kids. Quotient rule. Where do we start? Low. 5 cotan x plus x over 4. Ooh, here's the fun part. D high. I got plenty of room. I don't know. All right. What about d high? It's a sum, so you are allowed to take the derivative of each term separately. Okay. The derivative of tan x is secant squared x, plus the derivative of secant x is secant x tan x. Okay, I got to start getting smaller. I'm never going to fit this. I got to move it over a little bit. Why don't you just do what I'm doing if you don't have room? Just move things around. All right, so we have low d high, then what? Less. We got the high, tan x plus secant x. D low. Yeah, the derivative of the first term, you have the 5 times negative cosecant squared x. So negative 5 cosecant squared x. Oh boy. Negative 5 cosecant squared x. That's the derivative of that. Now the x over 4. You guys see it's 1/4? Well, that's the same as 1/4 x. So don't use the quotient rule to take the derivative of x over 4. That's 1/4 x, which is plus 1/4. All over. Well, that's squared. It's right here. Right? Yeah, so we're leaving that. We're going to run. Yeah, not touching that. Yeah. What? This is too easy here. Yeah, that was it. I know, they're disappointed. Sorry. Oh. We got it, all right? That's it. All right, 9 is just like, a little breath. What is 9? Minus sine x. That's good. Yeah, no, it's too easy. Oh, wait, I missed one. There's a 10, right? 10. Oh, that's supposed to be multiplication. I don't know what that is. So you're taking the derivative of 2 over x times tan x. Now, we could leave it like this, and we'd have a product. Can we put it together? Can we just write it as one quotient? Before we even take the derivative, I'm thinking, why do the product rule and then have, we could, but if we just write it as 2 tan x, over x. It's not as bad. You know what I'm saying? Yep, got to use the quotient rule. Hey, can we cancel that x? Oh, yeah, that's not multiplication there. Not a factor. Not a factor. Whoa. All right. Low-y high. Let's do this. Low is x. D high. 2 secant squared x. Good. Less high. 2 tan x. What's the derivative of x? Uno. All over x squared. Can I cancel that x? No. Nope, it's not a factor of the whole numerator. Don't do it. I'm going to keep it. All right, now, so we're done with that. I want to show you something that happens with when you take derivatives of sine and cosine. We're going to start with sine x. We're going to look for a pattern here. If you have y equals sine x, what would the first derivative be? What's the derivative of sine x? Cosine x. Okay. Now let's get the second derivative, the derivative of cosine x. Negative sine x. Okay, take the derivative of that. Negative cosine x. Let me just see what we have so far. So we started out with sine x, took the derivative, we got cosine x, took the derivative, negative sine x, got negative cosine x. Now let's take the derivative of negative cosine x. We're going to be back to positive sine x. So the fourth derivative is sine x. Okay. Take the derivative of that. Let's get the fifth derivative. Cosine x. Okay. Negative sine x. Take the derivative of that. Negative cosine x. You see how it's repeating? It's like a cycle of 4, right? What if you studied, think of your mathematical history, of what you've studied, there was something occurred in a cycle of 4 like that and just kept repeating. Yeah, remember powers of I? Like you'd have to get I to the 23rd, right? You divide by 4, but you didn't care how many times 4 went into that 23, right? You care about the remainder. So I to the 23rd, or whatever I said, would be the same as I to the 3rd, because that would be the remainder when you divided that exponent by 4. So let's say, so if you notice here, the 0th derivative, the function is also known as the 0th derivative, the 4th derivative, the 8th derivative, all those would be just sine x. Okay? What do you think the 21st derivative would be? So it would be the same as the first derivative, so it would be cosine x. You see how we're doing that? So if you want to know any derivative, let's say if I have y equals sine x, and I want to know the 32nd derivative, I'm just going to put a 32 here, okay? It would just be the same because the remainder, when you divide 32 by 4, you don't care if it was an 8 times, the remainder is 0. So it's going to be the same as the 0th derivative or sine x. See that? You've got all those little pathways in your brain already. You can just use those little, your brain is like a rainforest, and somebody's already macheted like a little path through. When you had to learn that, you've got a little path in your brain. You can basically use that same path. You've kind of done it already. All right, so now, I have one little thing. The homework tonight, I'm going to get rid of one of them. I know. Because it's just, you're going to look at these and think, oh, it's going to be great. It's not just going to be getting the derivative. Oh, no. Oh, no, no. It's going to be like, write the equation of the tangent line, which you need the derivative for. Or even better yet, how do you find out where you have a horizontal tangent line? How do you get the location of a horizontal tangent?
0.
So you have to get the derivative and set it equal to 0. And then once you know the x-coordinate, you can plug that into the function to get the y. So if you want to know where a graph has a horizontal tangent, you got to first get the derivative, set it equal to 0, and solve for x.
Let's don't say we did. Yes.
No, just you have to wait till after class to start your homework. Sorry, we don't have enough time today. If you want to take a picture of the problems in the math book, I have extra copies back there, the green one on top. If you want to take pictures now so you can work on it before you get home, maybe in your next class or something, go ahead. Oh, we can call this bye.